Hello YouTube, in this video I'm going to be showing you how to build a portable solar generator. Now you might be wondering, why do I need a solar generator? And you can use it for all kinds of things. You can use it for like if there's ever a disaster scenario, the grid will be down, so if you have a solar generator you can use that to power your devices. You can also use it for camping or for other outdoor activities, or like you can use it around the house, or like if you want to charge up like power tool batteries in your shed, or listen to a boombox or whatever. It has tons of uses. So, you might be wondering some of the features that this solar generator has. So, let's start on the side. Here's where you plug your solar panel in. I have this wire coming off the solar panel, and it has a connector on the end. This is just a normal barrel jack, and that can plug into the side, and that's how the solar panel connects. Here we have a USB charging port. Plug in your phones, tablets, power banks into that and charge those. Here's the switch right here. This is the switch to turn the inverter on and off. And the inverter converts the battery power to house power. So, and I don't want to have it always on because it consumes a small amount of power. So I have the switch there so I can turn that on and off. Here's the outlet. Now the thing about this outlet is it's actually a Christmas light outlet that came off the end of a broken string of Christmas lights. And I just use this adapter. This is like a travel adapter. And this will accept both non-grounded plugs and grounded plugs. And you might be thinking, well, that's kind of unsafe. It's not polarized, and it defeats the ground. Well, if we look here at like normal house power, this is what your normal house power looks like. 120 volts. And so this 120 volts here, 120 volts here, and this is neutral. Now, it wants to, electricity wants to find the opposite, basically. It's attracted to the opposite charge. So if we have 120 volts, it wants to balance out, so we'll flow to neutral. Now, between the 120 volts and neutral, that's where you'd connect your load, so the electricity would go through your load. But if we look at the power that the inverter makes, you can see actually out of each prong of the plug it makes two different sine waves, each 180 degrees out of phase, and these two are about 60 volts or so, and so basically there is no polarity. There's no wire that is at 0 volts, like with standard house power. Both of them are live, so there's no problem with polarity. Now with the grounding thing, the inverter, the ground prong on the inverter is just a dead spot, so it doesn't really even matter with the grounding. Because the inverter doesn't need it. Here's a 12 volt receptacle. This is like one you'd find on a car. Now it's current limited to 2 amps. Not very much. That's not a lot of current, but it's fine for charging cell phones or tablets, or running like a CB radio or a small 12 volt television. It's currently limited to 2 amps because it's going through my charge controller, and that provides over discharge protection so that the battery doesn't doesn't get damaged by depleting it too much. But the charge controller can only handle 3 amps. I'm protecting it with a 2 amp fuse. So if you pull more than 2 amps, the fuse is going to blow. So this one you can only do up to 2 amps. Now these side terminals are for like if you want to connect an external battery charger or an external battery bank, or it's fused at 15 amps, so you can pull up to 180 watts out of that, which is quite a lot. Well, not a whole lot, but it's about if you have like a 100-watt light bulb and well, yeah, and then there's the other 12-volt receptacle. This is also like one that you'd find in a car. This one is 10 amps, and this is for higher current devices. Like if you have a 12-volt compressor, like a 12-volt tire inflator, or a 12-volt vacuum cleaner, or something that consumes more power, you can connect it here. Now the thing is about this port, and also with this one, these aren't going through the charge controller, so you have to make sure that you don't deplete the batteries too much. If you do, you can decrease the lifespan of your batteries. So you want to make sure that you're not depleting your batteries when you're using devices through these ports. And if you're using a low current device like a phone charger, it's best to plug it in here so that the charge controller will automatically disconnect the batteries if you discharge them too far. You might be wondering how I built this. So, if you look on the side here, I have these hooks. These are just command hooks. What the point of these is just to keep the lid down so that it doesn't just pop off. And then, so this one I can pull up. It will release the rubber band. On the other one, there's hot glue here, so I can't remove it. So you can never lose the rubber band unless it breaks or something. Now I'll take off the cover. So inside I have a 7 amp hour battery, and it's wired in series with a 1.3 amp hour battery. Now basically when you wire batteries in series, you increase the capacity. You wire them in parallel, you increase the voltage. But I want this to be a 12-volt thing, because, you know, I want to be able to run 12-volt devices off of this and charge it with a 12-volt solar panel, so I wire them in parallel. And also, since the batteries are different capacities, I can't wire them in series. Here I have the charge controller, first connected to those batteries is this is a fuse. This is like a automotive kind of fuse, like in a car. It's a 15 amp fuse, and that protects everything from overloading and short circuiting, which could damage the batteries or the wires. Now, connected to that, we have the inverter, which is that red box that you see down there. So that's connected to the fuse, to the output of the fuse, and also the negative wire. So this is what converts the battery power to house power. Now you don't have to worry about over discharging the batteries. The inverter has that protection built into it. And then on the inverter, there's a USB extension cord. You see that plugged in right here, and then the other end is hot glued here, so that's how you can charge your USB devices. And over here, there's the same kind of Christmas plug. Over here, yeah, that's what that is, and came off a broken set of Christmas lights. reason I use these kind of plugs is this doesn't have to carry a lot of current anyway. The most I would pull off of this is 120 watts off this inverter, so these plugs are just fine. And it's low profile, it doesn't stick out really far, so that's why I use that. The switch for the inverter. I made a mistake here and I forgot to wire in the switch, but that's fine. I'll just correct that right now. There we go. So we got the switch. Now we also have here a charge controller, and it's this little white box here. And this is the fuse, and it's on the positive side of the charge controller. And this protects the charge controller from over current or short circuits. Now I use a 2 amp fuse because it's a 3 amp charge controller. That's the max it can handle. I would probably be fine if I just hooked it directly to the 15 amp fuse. It'd be protected from short circuits, which are probably the worst kind of failure. But it wouldn't be protected from overcurrent. If I tried to plug in a 10 amp load, it would run it just fine until the charge controller breaks. So you gotta have a appropriate fuse here, so that if I plug in a load that's too high, the charge controller the fuse will blow and the charge controller will be protected. Connected to the charge controller, I have this plug. This is for the solar panel, and that goes to the solar input right here of the charge controller. Battery input is what's fused. Then the load goes directly to the socket, and here's the socket here, and it connects to the load terminals. The positive and negative terminals go there. And then we have the socket, the high current socket, that's directly connected to the 15 amp fuse. And that's over here. The socket is hot glued over there. And I hooked the socket up to the main splice with all the different loads. So now my socket is protected by the fuse too. And this connection is also going through the fuse. And this has like a couple different purposes. I can connect a 12 volt battery charger to this and then charge it with house power. I could connect a load that takes more power than the socket is rated for and connect it there up to 15 amps. Although if I'm drawing 15 amps from here, I can't draw any power from the other sockets because the whole thing's limited to 15 amps. I can use this to, so external loads. I could hook up an external battery to this, like another 12 volt battery, and I can connect it there, and the charge controller will still charge it up, and the battery will add more capacity to the system. I use sealed lead acid batteries because they're cheap, first of all. They're relatively safe if you can, like, lithium ion batteries are like the kind that are used in phones, and the problem with those, they're expensive. Not just for the battery. I'd have to buy a more expensive charge controller. And also I'd need like all kinds of protection circuits like overcharge, over-discharge, overheating. I'd have to have all kinds of protection circuits on that because those batteries are very sensitive, and and also they're not very safe. If you heard of the Note 7s or the exploding hoverboards, that's because of lithium-ion batteries. So I wanted this to be easy, cheap, and safe. Now, these sealed lead-acid batteries are heavy for the amount of power that they store, but they are very, very cheap. One of the things though is you have to use sealed lead-acid batteries if you want to use this thing indoors. I know there's flooded lead-acid batteries, which are like the same kind of batteries that are used in like cars and RVs and boats, and those are fine because they're ventilated. But with these sealed, but the thing is when those kind of batteries are charged, they emit hydrogen gas, and hydrogen gas is explosive. So you don't want to use flooded lead-acid batteries inside your house because you can't vent them. But sealed lead-acid batteries are completely sealed, so that means that they don't emit hydrogen, so they're safe to use indoors. And also these batteries are they don't need the water replaced like flooded batteries. And another plus in this case is the battery is mounted on its side. You couldn't do that with a flooded lead-acid battery. The acid inside would leak out, but with sealed lead-acid batteries you can mount them in any orientation. Now, to keep all the parts from like sliding all over, because if I'm like putting this in my camping bag, I might want to put it on its side, or so I didn't want the parts to be like loose inside of here. So what I did is I got some Velcro and I Velcroed everything down. Now that makes it so if I need to take things out, I can easily do it, but it is pretty strong, especially since most of the time that I'm using this, it's right side up. There's always pressure on the Velcro, so that means that the Velcro is always gonna stay strong. And for on the outside, you might be able to tell I used a lot of hot glue. I could have gotten away without using this much hot glue if I would have got things that can just kind of screw down easier. The thing though about the hot glue though is that it kind of helps to make a better seal. If I'm using this when I'm camping and it gets a little bit like rainy, it won't get like all wet. Hopefully. Now, I wouldn't recommend keeping this thing outdoors all the time, or like leaving it outside, because this kind of plastic might degrade in sunlight, and also it's if there's a lot of standing water or rain that's coming down really hard towards the plugs, it could possibly get water in it. So you don't want to leave it out in heavy rain or in or for long periods of time outside. But this is slightly weatherproofed. Now, if you want to, you can get like an ammo box, and you can put this whole system, you can build a solar generator inside an ammo box, and that will make it so that it's waterproof, because those things have a seal. If you do a good job keeping the components all sealed up, you can have a fairly weatherproof solar generator. One thing I forgot to mention about this is if you build one of these, I'd recommend building it in a slightly bigger container, because this system is so easy to upgrade. I could put in more batteries. I could put in bigger inverter, bigger wires to carry more current, more outputs, a better charge controller. I could upgrade all this stuff. I kind of overestimated the size of this container, so I don't really have much room, but if you build one of these, you might consider doing that, using a bigger container so that you can, in the future, possibly upgrade this. One thing is, if you decide to get more outputs or a bigger inverter, you're going to have to use thicker wires. At 12 volts, 180 watts is 15 amps. At 120 volts, which is normal house power, 15 amps would be 1,800 watts. So 12 volts, there's more amps, and since it's lower voltage, a voltage drop is going to have more of an effect. So you have to use thicker wires if you're going to use more loads. I used 16 gauge wire. It's capable, like when it's used in extension cords, they usually advertise 13 amps. Usually when it's used with 12 volts, they'll often fuse it at 15 amps, and it's such a short distance. The longer the distance of the wire, the more current will be lost in the wire due to resistance. So if you want to make really long wiring, like from your solar panel to your solar generator, like if you're going to put your solar panel far away, you want to use thicker wire. Because thicker wire will have less of a voltage drop over a distance, and it will also get less hot. If you put too much current through a wire, it'll heat up, and if you pull too much, you can melt the wire. Now, these aren't really thin enough to have that happen, but like if I was to use like really thin wire, that wouldn't be good. So, and it would be very inefficient. So you want to, if you want more efficiency, you need thicker wire. Now, to give you a rough estimation about how much power this stores, it's 100 watt hours. Now, in a perfect world, 100 watt hours would power a 100 watt light bulb for an hour. But because we're using lead acid batteries, especially, the higher the discharge rate, the less capacity. So these are rated at a 20-hour discharge rate, so that means that it would be about 0.4 something milliamps would make it a perfect 8.3 amp hour battery. But with like if you're like, let's say you're charging a cell phone, that you will get like maybe the full, depending on how fast your phone charges. If it charges slower, you might be able to even get the full capacity out of this. If you're using like something huge like a 100 watt light bulb, it might only run for like 30 minutes, even though it's a 100 watt hour battery. Because of the higher discharge rate that a 100 watt light bulb will put on this, it'd only run for probably about 30 minutes. But 100 watts is a really big light bulb, and that's with an incandescent light bulb, which are terribly inefficient. So if you use compact fluorescent or LED light bulbs, say I use a 10 watt LED, they'll run for about 7-8 hours before the battery dies. I could run, refrigerators actually are getting more and more efficient. So if I was to get a desk height refrigerator, Energy Star compliant, that only takes 24 watts since it only runs probably about a quarter of the time, I could run it for possibly up to 12 hours, a little mini desk height refrigerator. But if I have enough solar, I can run it 24/7 because I would be replenishing the energy that I use. And so this will charge a cell phone about 10 to 14. Maybe if you're lucky, if you have like a dumb phone, like 20 times. It'll charge my power bank about 3 times. Charge a tablet maybe about 5 to 6 times. Run a little 12-volt TV for about 7 hours. It'll charge a laptop depending on what kind of laptop. If you have like a top of the line gaming laptop, that might charge maybe half the way. But if you have a netbook, that will charge possibly a few times. It also depends on how fast your charger charges your computer, because if the discharge rate of the batteries is higher, then you get less capacity. So theoretically, the slower the charger, the more times you'll be able to charge it. So now I'll show you this system powering some different devices. Alright, so now I'm going to do some real world testing with the solar generator. So I'm going to get the cable for the solar panel, and I'm going to connect the end to my multimeter, which is right over here. Now that's displaying voltage, so I'll get the end of my cable, which is connected to the solar panel. And if I hook this up, it says 21.59 volts. Now if I hook it up to the amps, this will be the current. I'm getting 1.4 amps, so I'm getting a lot of current off the solar panel. So I'll plug the solar panel into the solar generator, and now let's try to power some stuff. So I'll get first I'll start off with something easy that I'm sure the solar generator will easily power. Let's start off with a power bank, a portable power bank. Plug that in, switch on the inverter, and then on the other end, power bank. Sorry about the shadows. And I'll plug this in right here. And now, if you look at the little lights, you can see that the power bank is charging. So now, so that works. Let's connect something else. So here, I got a 12 volt, it's like a DVD player, but it also has an auxiliary input. So I got my 12 volt TV here, and I've got a cord. This is just a cigarette lighter cord that will work with it. So on the side, we'll plug in the power cord, 12 volt adapter right in here, and then I'll plug in the plug into the low current port. This only takes about 10 watts, so it'll be just fine with the low current charger. Just plug it in and switch it on. And we can see that it's lighting up. Now, I'll connect a power bar to the solar generator right here. And I got a power bar here, so let's see what else I can power with it. Let's make sure it's switched on. Let's get a compact fluorescent light bulb and plug that in. And you can see there, it's kind of hard to tell, but it's lighting up. And this is a 13 watt CFL. I'll get a 17 watt fan. I'll plug that in, and we can see that the fan is starting to spin. Now, on camera it looks like it's slow, but in real life it's putting out a good amount of air. But I think this is on the low setting, so let's turn it up to the higher setting. Now it's on the high setting, and I can really feel some air moving. Now I'll get my last, well, I'll get another device. Alright, here I got a 20 watt boombox. And I'll plug in my cable to the back of the boombox. It's right here. I'll plug that into the power bar as well. Now let's see if it plays. It plays. So now I gotta stop it because it's copyrighted material. So the last thing that I'll connect, well, I'll connect a 5 amp car vacuum cleaner. So here's the vacuum, and now let's plug it into the high current port on the solar generator. If we look on the side, it's just a normal like cigarette lighter port. And if I plug that in, go over here, and I turn this on, it runs. It even sucks up some sand, so I guess that works. So, that was my solar generator that I built. Thank you for watching, and I hope you like, share, and subscribe.